On barbecue, we gotta be any sauce.
I know, right? See, I just take it.
Please tell me it's gonna be 85 and sunny.
God, I wish. We've been to LA.
In New York, heater I gotta work with. Even by our standards, didn't do it. Too cold.
Very cold.
No, it's not like this. I haven't been out across the country yet. Once in a while. I did that every year since I graduated.
What is summer?
Just a couple times a year. I hope you're out there. I know it's good.
Although I have a feeling it's not doing you can no, this is happening. Why? People like all over the state. I've never heard of that. Who do they think is gonna clean? This is what I don't understand. Yeah, no. They think the direction is not clean up for them, and I don't think it's the people that are like, well, right. Awful. They probably are not the people that they don't
Right. Yes.
But do they think they're doing it for everyone?
Well, that's so sad when those facilities are there, and they get, I think you know, it's dumb enough to do that.
What is that?
You know, there's
Our dollars and privileges. Because people like,
what do they do? There's one they lock.
yeah, there's just a lot of people. But they have the.
How frequently do you guys use?
I mean, the actual like building
Why would you want to do that? I think you're own presentation.
No.
And even more reason.
What's the rule in your apartment? What?
You got papers or is it? Well, we have a digital out there. So, I don't know
When Josh was looking for fantastic,
I do.
Yo,
So that's like in our house.
I'm nervous. I have to get all the explanations correct.
That's what Happy Mary. Oh, no. No, it's worked out pretty well. That'd be one.
I did. I have
What is left for a little bit? I just not comfortable.
Yeah.
Really? I'm just not comfortable with, I mean, I do it.
So our rental house is like this little back, but we have a room that's built into our deck. Right outside, that you just like literally walk out the door from the kitchen. It's there, so we grill. Yeah.
Oh, I grill in the winter.
Well, we tried to grill on Christmas. So probably just so early, so this morning. And just so you all know, I did look out the window there and see
He's your house.
you know, you see the water tower?
Oh.
Right near my house, my yard back in the corner. So, every Christmas Eve, there's one I come up with Christmas Eve, Friday at work. And nobody grills salmon. And my house was built. As I was coming in from work, oh no, so gross. That, something's living in our fridge. Oh, I'm right too, so I went out there, and he opened it up, and I looked, and all the while, mouse family. I think so. And I think it, yes, it was in one place, so we all done. So he, I mean, I took this cover off all the, and then 20 minutes over there, we had. We had his camping grill, got to the basement and went out in front of the front.
One day,
So over the whole eye.
of course, it's gonna
I
get
kept trying to get a picture, but probably squatters. Squatters. I'll probably be contaminated one more time before we do it, so.
Yeah.
He's done it, but I'll.
That's good. Here you go. Ready.
What's that? Oh, yeah, I did. Yeah.
Everybody good? Alrighty, hi everybody. Thanks for coming again this week. This week we have Chris Melhauser, who is a graduate student, PhD candidate in the Department of Meteorology. He's going to talk a little bit about modeling and data assimilation before we get into the briefing here. So it should be a good one. Thanks, Chris.
Thanks. Yeah, again, I work with Fuxing Zheng here in the Department of Meteorology, obviously. I'm working on predictability and tropical cyclones and data assimilation, so kind of a combination of everything in there. And I notice we have Rich here, who's the king of ensembles, and we have some data assimilation folks. So hopefully this is a good, just general primer of going through some basic differences between the way the GFS and the ECMWF are initialized and how that is going to impact future forecasts and forecast performance. So I'm briefly just going to go through and just look at who has the general upper hand. If we look at some basic error statistics, which one on average is better? Some fundamental differences between the model and the data assimilation. I'm really going to focus on the data assimilation portion and then discuss some possible future upgrades, which I know as what's found online, so there might be some more insider information that that is available. And then we'll discuss about the weather and the possible little storm system that come through Sunday, and then a nice little precip making storm on Tuesday into Wednesday. And also some slightly warmer temperatures. Relative is the key. So just to start off, this is actually the plot of years on the x-axis, root mean square error on the y-axis, and it's the northern hemisphere 500 hectopascal geopotential heights verified against dropsondes or observations. And so it's the three different models. I've plotted the Canadians, the Americans, and the Europeans, red being the Europeans and green being the Americans. And this is the root mean square error, so a lower error is generally better, or is better, in reference to this forecast. And so what they are, just take the 10-day forecast, and you subtract out, take and calculate the error from the observations, and then average them over the 0Z forecasts every day over each month, and then just plot that error over the time series year, and that's what's plotted here. Now, granted, I don't have the UK Met Office, and there's some other ones, the Japan Meteorological Association. If I get that right, I might not. But there are a few other global models that are definitely leaders too that are on here, but these are the ones that we most commonly think about here in the US. And what I just want to point out is generally, on average, if we look through time, this is 500 hectopascal. Again, you can look at this at different variables. We move down to the lower portions of the troposphere, where you're going to be more influenced by moist processes and mesoscale features. You could still see a same signal in general that the EC generally has lower errors than does the INSEP model or the GFS. And just note,
it makes a little improvement, it would appear.
Yeah, in the 500 hectopascal heights. Yes, I agree. I have the mean sea level pressure I can show you at the end that you can see a drastic difference that goes through. So this is just in general on average. I just wanted to give the picture that even in just in the statistics over time, there's definitely on average leading on that for the GFS or for the EC. But just to note, if you actually look down at some of these times down here, there are a few points where the GFS does better. So this is the long run average. We're not looking at the small variability. Sandy is a great example where the EC really predicted this storm very well to track 7 days out in advance, and that's where we got some media credibility that went along with it. Now, if we look at and compare, now let's look instead just the lead time hours. So this is the same variable, but let's just look at a period over the last November, December, and January average. And we have on the x-axis the lead time, so 24, 48 hours, and again the root mean square error. This is a little more clear on just the shorter time period on the errors. Again, lower being better, and the GFS pulling, or the EC pulling ahead of the GFS at all lead times out. Now again, if you look at different variables, mean sea level pressure, GFS does better at the longer ranges, and there's different variables that it does. But on average, this trend continues. So, looking at some key differences. Now again, there are different modeling constructs, different modeling systems, and if you look at the different model components, parameterizations, the boundary conditions at the surface, and the dynamic solvers themselves are different. But in general, the major first order differences between the two are the resolution of the model. So a higher resolution model, you have to solve for more equations on more grid points, and it's going to cost a lot more computationally to run. Now, we recently, in January, upped the resolution of the GFS to 13 kilometers from 27 kilometers for the 0 to 10 day forecast, and then 35 or 32 kilometers, I believe, from the 240 to 384 forecast out. Now, for that, that's the deterministic member, and we also have the ensemble component of the forecast system, and that is 21 members, and that was up to 35 kilometers from the horizontal, 64 in the vertical. Now, if we're noting between the two different systems, the EC has slightly less, I mean, we're talking the same order of magnitude here, 16 versus 13. But this has been implemented since 2013, and they've been consecutively ahead on resolution. They have a lot more computing resources, and they have less products that they're running than INSEP is for the same, I guess, product system that we have. And the ensemble forecast, in general, they run for their ensemble 51 members. Now, when we get into the data assimilation component, they actually use a smaller subset for the hybrid system, which we'll talk about here in a moment. But overall, their ensemble forecast itself is also a larger sample for estimating the uncertainty around their ensemble prediction. So looking at between the two centers, resolution is a big one, but coming time into, back to what I do, I'm looking at the data assimilation component. And currently at INSEP, we run a 3D VAR hybrid component, and I'm going to explain these in a minute, whereas the EC does a 4D VAR hybrid data assimilation system. And the 3D and 4D, we're actually describing spatial and then time. So we have the spatial component for the data assimilation, but they actually include time when we're looking at the ECWF version. So zooming in on it, of course, with any time you have data assimilation, you always have to bring in the board. No questions asked. So it's achieving perfection. And so the idea is that you want to optimally combine observations and numerical weather prediction model data and come up with the best initial state of the atmosphere. Now, any numerical weather prediction is going to be a forecast, so how well your initial condition state is going to be directly impacted on how well your forecast will be out in the future. Now, we can get into chaos theory and predictability issues at shorter and longer scales, depending on what you're looking at. But in general, a better initial condition will yield a better forecast. So we want to optimally come up with the best initial conditions. Now, we want to produce the best possible estimate of the current state of the atmosphere. And optimal and best, these are going to be used statistically. We're going to define them as the maximum likelihood of, or the minimum variance, and it's something we can talk offline. But in general, it's a statistical way of defining what is best and what is optimal. And so, of course, we have John Luc Picard on the board, and then Locutus at the end when he's assimilated. All right. So the idea is what observations? So we need to take observations and put them into the forecast model. So this is a nice graphic from EC that they've kind of highlighted a lot of the main components. So satellite observations, wind vectors, which this was actually just included in the GDAS system in January, where we track satellite cloud motion and then use that motion to drive wind speeds, and that is actually inserted into the models. We also have dropsondes. So at HS3, back over the summer, the global models actually incorporated all the dropsondes that were being dropped from the HS3 drones that were flying over hurricanes, which is kind of cool. But then also different, you have ships, you have the basic stand, synoptic land and weather balloons, and then ACARs, so the pressure and temperature measurements that are on the side of aircraft that you can have vertical profiles of these through the atmosphere. So the idea then is we want to combine the observations with the model background data. And so pretend we have, for example, just two variables, or two observations. One is an observation, and one is a model background estimate of the temperature at State College. So we're just looking at an observation, a measurement from a thermometer, and then what the model is predicted at State College. The question is, how do we optimally combine these two data sources? And so we combine it based on how well we trust each data source. And so I've kind of diagrammed this here by the size of the circle. Generally observation, I'm assuming here that we trust it more, so it's going to be a smaller error. And the TB, the background, is a larger error, so it has a larger circle, and we trust it less. And so the error associated with the observation and the error associated with model forecast that we're using as the model portion of the combination, that will determine how well we weight it and how much weight we put to the observation and how much weight we put to the background. And so if we trust the observation more, it's a better measurement, we're going to put more weight to the temperature of the observation versus the background. And that will end up giving us our temperature. And so this error associated with the model forecast, so the error associated with the observation is just, we have a temperature measurement, and it's going to have some random errors that are around it. It's not going to be exactly representative of what the atmosphere is at that point. But we also have the error associated with the model forecast or the background, the TB. And this background error actually can provide us a lot more information than just how much we should weight between the temperature, or how much we should weight the temperature of the background and the temperature of the observation. It can actually help us bridge a gap between variables. And so if we observe the wind at a certain point, we can actually improve the temperature at the same point. And so we can use observations also that are not within the model. So if we have radial velocity observations, we can use that, incorporate that into the model, and then update the wind U and V components and the temperature as well. So these background errors are very important and are somewhat, you could say, magical, in the sense that we can take one observation, totally irrelevant, and use the structure that's in these background errors to update a different observation. So really, if we want to do this as an example, this always took me forever to figure out, the correlations in the background itself. Like, how does this really work? So a simple mid-latitude example would be an idealized cold front that we have in the mid-latitudes in general. So on the backside, pretend we have a northwest wind, it's cold. On the fronts, we have an east-southeast wind. Ahead, we have warmer conditions. And so generally, if you inspected that you had a stronger wind component here, you'd have stronger temperature advection bringing colder air, and therefore you'd expect a drop in temperature that's higher. So there's a correlation there between the temperatures, the wind speed, and the temperature derived because of that background flow. And so if we take a temperature measurement, or a wind measurement, at this point, we can then use that relationship between the fact that we have a higher wind speed, would tend to indicate a higher temperature or a larger temperature advection and a drop in temperature to up to your temperature observation. And we can also do that spatially, so not at just one point. You can update different observations or different model grid points at other points around the grid as well. So it's not just space or at one point, but you can do that across in space and time. All right. So the big question is, operationally, how are these errors generated? And so we can use the ensemble, this is coming in important, where we can get model forecasts valid at the analysis time. And so when we're trying to get that best current state analysis, we have an ensemble that we then use that to estimate the uncertainty of that background error. Or we can do model forecast error climatology. So all we're really doing is taking the model and taking the 24-hour minus the 12-hour forecast and coming up with a climatology for that specific model. And we use 12 and 24. It helps to bring in the diurnal cycle. It helps to get a lot of patterns that then we can build up these correlations of this air structure that helps us, again, weight the temperature and the background between the observation if we're just doing that, or spread that information above. And so the big two, the ensemble and then the variational methods, the variational will use this climatology and the ensemble will use the obvious ensemble component. Now, I think I'm doing good on time. So the idea between two, there's kind of these two, when you have any kind of prediction problems, you can filter something, you can smooth something, or you can predict something. And so the filtering problem, let's just generally think about it as we want to use observations up to the present point to obtain the best estimate of the current state. So we have our observations and we want to use everything up to a certain point in time, so let's say when we're doing our analysis, to come up with the best estimate. Now this filtering assumption assumes that observations are valid at the analysis time. And so operationally, what we'll do is we'll make an analysis at, let's say, 18Z, then we'll run that forward using the forecast model to 0Z, and then incorporate all observations within that period from the previous 6 hours up to that point to come up with that best estimate. But to do that, we have to assume that all observations are valid at the analysis time, even though they're not valid at their correct time in space or in the time dimension, right? So we're taking all of them and assuming they're valid at a certain time, and then incorporating them into the model. And so by doing that, then we come up with analysis, run it out for 6 hours, and repeat. And so this is what you might think of as the ensemble Kalman filter or the 3D variational method. And so again, you're just taking observations and spatially, we don't have a time dimension in it, and coming up with the best estimate. Now, smoothing processes are we're using observations up to the present to obtain the best estimate in the past. And so you're smoothing based on future present, if you want to think about it this way, based on future observations up to the analysis. And so we make our analysis time at 0Z. We use observations that are up to 6Z, so we're running this in the future even though the observations have already occurred. And then what we're doing is this allows for observations to not be used at the time that the analysis we're making the analysis, and we can use observations that are not at the analysis time. So for example, we have our background that we have estimated at 0Z, and we have our observations through this time assimilation window. And so what we do is we run something that we call, I'll leave it as a black box, it's a simplified model of the actual forecast model, and then we can run that forward and then use that information, the errors, the climatological errors then, to update the temperature and go in the future and then back and into the future and back. And that is how we can then update the analysis at this time. And then we run it again 6 hours ahead and repeat. So the two basic differences is one is spatial, we don't have the time component, and the second one is we have the time component, which helps to improve the analysis because we're taking in future information into the current point. And so these would be known as the 4D variational method, or the Kalman smooth is another version that's been made. And so research-wise, is there a superior method? And yes, the 4D bar has been shown to be superior to the 3D bar, the 3, so we're taking in that time component. So it's actually a better data assimilation methodology. But it requires a large amount of maintenance. You have to create this black box model every time you make changes to your actual forecast model. And it also requires a lot of computing resources because you have to run that model back and forth, that simplified model back and forth every time you're trying to bring those future observations into your certain pipe. Additionally, variational methods are only used at climatological error. Remember, we calculated that from the climatology of the model. And so there's something that's not included in that is the actual flow of the day. It's a climatological background error. It's not actually what's occurring at this moment. The ENKF, again, was just an example of the filter, has been shown to be superior to the 3D bar and uses the errors of the day, though. So we're taking the ensemble at this analysis time, and we can actually calculate the errors of what we're seeing in the actual flow. So that cold front is actually going to be evident at that time when we're updating. And so that is going to bring us additional information about, we call it the errors of the day in the data assimilation community for assimilating those observations. But they have their own problems, such as the number of ensembles that should be used to correctly assume or correctly estimate those errors. So the question is, why not just use both? And that's actually what's happening at INCEP and EC. There's a hybrid ENKF, so what they're doing is they're taking the climatological errors and then the background errors associated with the ensemble, and they combine them together to give a better estimate of updating, so that there's a better way of taking the temperature and updating all the different other fields. And at the EC, they're doing the same thing, but they have a 4-dimensional. They're using the 4D VAR, and this is, again, very computationally expensive. And so the argument on the improved initial analysis is based on this idea that they're using a 4D bar versus a 3D bar, which is shown to be a better way of updating and creating analysis. So INSEP currently is working towards incorporating something called a 4D ensemble bar. So we're going to take the 4D variational method, but we can actually use the ensemble as well to get rid of this black box model that you have to do. And so that reduces some computation and also reduces the need to keep updating this model. And so it's a beneficial way to get around a lot of problems that operational sensors have with the 4D bar at the EC and WF. And so the EC, I couldn't find any information. They're kind of in a black box. So that's that. So with that, we're going to go on the weather. So I still have 11 minutes, and I figured I would wait and then ask questions at the end. But I just wanted to clarify just kind of what's the difference between the initialization that INSEP needs to be up, and these are very big components that help to dictate the performance of future forecasts for each center. So does that kind of make sense? Is that general gist? Cool. Okay, so now if we jump to the weather, which is what we're all here for. So this is a 24-hour loop of the satellite imagery. And I always love seeing, well, not love, because it's not fun to be in the cold, but seeing the nice surface air temperature showing up on the IR. So some really cold air up over Canada, and this has been what we've seen for the last month, so nothing surprising. But we have that system that moved through the south, bringing snow all the way from the northern part of Mississippi up through DC, and it's currently ejecting off to the north and east. There was a big concern yesterday with Atlanta getting snow, and so there was a winter storm warning, I believe, that they issued for 2 to 5 inches, and it ended up no snow falling in Atlanta, but just a little bit to the north. But I guess given the big size of Atlanta in general, that was probably a prudent warning based on what happened last year in general. So we have that system moving through. We also have another system here to the currently over the Great Lakes that will bring a quick dusting to the west, northwest central mountains over the next 12 to 18 hours, and then eject off to the northwest as we move on into the weekend. So looking at the 500 millibar heights, what is notable here is we have this northerly flow, and so this is where we're having all this cold air still streaming into the upper plains. And so high pressure building in the northern plains that'll then move off to the north and east. We have a little wrinkle here that is part of this upper level system that's bringing that snow into tonight. But just looking at the surface analysis, there's that high pressure, and this is what's going to really dominate our weather for the next Friday into Sunday morning ahead of another system that will come through at that time and help bring a little bit warmer temperature for a little bit, but then also bring us some snow to the area. It looks most likely maybe a mix down along the Mason-Dixon line, but we'll have to wait and see on that. So looking at the current radar imagery, we had some snow. I wanted to leak this. We had some snow over Harrisburg earlier in the day that showed up, and in the Lancaster Valley and a little up in Bradford. But off to the west, it looks like it's actually died down a little bit of the system that will move through. We're going to expect this to show in western and the northwestern central mountains where we'll have some snow tonight, but that will be a very light amount, according to maybe an inch along the higher ridges and up in the west central Alleghenies. And looking at surface analysis, this earlier looked a little bit better, but again, we can see those surface winds. We had more easterly components helping to bring the cloud cover over to the east, but now we're getting into the regime where we have more northerly flow at the surface, helping to bring cooler temperatures, and this is going to be the trend over the next 24 to 48 hours. The story, though, is over the weekend is the slight moderating of temperatures. What are you going to call it? It's relative. Anything's better than what it's been. So on Saturday, we'll still have high temperatures that will be comparable with our normal low temperatures. But over the next 48 hours, 24 to 48 hours, we're going to have, so we see the upper level wind pattern here. And so we have confluence over the northeast region, and this is indicative of that high pressure moving through. As we push into Sunday, we can see now we have a much stronger southerly component to this, helping to bring warmer air up into the central part of the northeast, or if we move up into the southern portions of Pennsylvania. So if we keep that moving through Monday and into Tuesday, we have another system that'll push through Sunday night, little ripple in the jet stream there, into Monday, And then we have a nice rebound, southerly component of the winds, and we'll get some warmer temperatures into the western portions of Pennsylvania Tuesday into Wednesday ahead of this system that'll bring primarily rain to the south and east, and we'll have more of a mix if we move. And it's going to be kind of, the big story is what kind of precip's going to set up at this time. But the big story then is just the southerly component to this, that we're actually no longer getting that northerly cooler air moving into our region. Given time, I'm just going to look at, this is the GFS ensemble. And so over the next 24 to 48 hours, we have this high pressure moving into our region, cooler air coming in behind. And with that, we're going to have lighter winds. So tonight into tomorrow, we're going to have cooler temperatures. This, again, is 2-meter temperatures, so it's not a direct representation. MOS is better. It's model temperatures, not MOS or anything that's been regionally massaged, I guess. And so we can see the temperatures that will get down. We're going to see temperatures in the single digits here in the center portion. We'll recover tomorrow barely up to the teens. We'll see teens across the central portion of Pennsylvania, a little bit warmer in the mid-20s down in the south and east, the upper single digits in the north and west. But the big thing will be Friday night into Saturday morning, where we'll have a nice drop-off in temperatures. We'll have clearing skies with the high pressure, lighter winds, and so this will help temperatures drop rapidly. We could be flirting with 0 in the central portion of Pennsylvania, and then a little bit in the teens in the southeast, and then below 0 into the northwest. But as we have that switch aloft in winds, and we're going to be bringing more southerly, warmer winds, we're going to have a temperature increase up into the 30s across Pennsylvania. And we could see up to, it's still below normal for this time of year, but anything's better than what we've had. And behind this next system, we'll have a little drop off, and then back up ahead of the next system, we can see temperatures in Pittsburgh up into the upper 30s, maybe even reaching 40, depending on how strong that southerly component is. So just as a quick representation of what we're doing, this is a operational high-res forecast, and I just want to use it to show where we're having these systems. So tonight we have this system with some light snow over the Laurel Highlands into western central mountains. And as we progress through the next 24 to 48 hours, that high pressure dominates with no dry conditions until we get into Saturday or Sunday, where we have precipitation moving in from the west. And this is going to move through Sunday night into Monday, and it'll be a lower amount of precipitation on average, 0.1 inches, maybe a little bit more into the southwest, into the Pittsburgh region. I'm directionally challenged a lot of times. And so we push through, and then we'll have that next system, which is going to be a lot more juice to it. It has a lot more moisture to work with, and we're going to have potential of a larger precipitation amount across Pennsylvania. And again, what's going to be the question is what that precipitation type is. And so if we look on the Monday night into Tuesday, this one is primarily going to be a snow event. We're going to have to look down at the Mason-Dixon line. This is the 850 mean temperatures, and so the 0 degree line down over the Mason-Dixon, so the ensemble mean here. And so this is going to be mostly snow. But as we move into the Tuesday into Wednesday storm, this is where it's going to be starting off as snow as we have cooler air ahead, but it'll eventually turn into rain as that warm air nudges through, and we could have a higher precipitation and then more rain and mix at this time. So it's going to be really what's happening with that vertical profile in temperatures that's going to dictate this. And given, so I kind of talked about that. There's 3 minutes left, so I wanted to leave some time for questions. I'll leave it at that, and we can ask questions and go from there.
Question for Chris? Anybody? Anybody have any questions?
Come on, just one. I can ask myself a question. I mean, I have 3 minutes. I can.
Yeah.
Yeah.
On the 3D bar you talk about, you said it's, and I know very little about the sort of the details or really anything about data assimilation. I was wondering on the 3D VAR, you had time steps, but you said it wasn't time dependent or didn't vary with time. What? I mean, I think I get what you're saying, but what does that?
So we're going to take all those observations and assume they're valid at the same time.
whereas 4D assumes a value.
There are different times, and so that's that black box that we use. So you create a tangent, linear, and adjoint model, so it's a simplified representation of the actual forecast model, and you run that to get information. That's how you propagate the information from the temperature time at the future back to the analysis time.
Okay.
And so that's where that comes in. So that's the primary difference. Okay. Well, thank you.
Great. Thanks so much, Chris. Thanks, everybody. We'll see you back here next week, the last 3 weeks before spring break. See you then. Thanks. That was really cool. It was different. So
Well, yeah, that's what